In your A-level chemistry, there are a huge wealth of procedures you need to learn and calculations you need to do, but there are also just quite a lot of key facts to memorise. This video is the first in a series that I hope will help you to ensure that you've thoroughly learned the facts listed in your specification, so that when you go on to do those calculations and applied questions, it's not your recall that's tripping you up. There's a link in the description below to all of the questions so that you can answer these and then use the video to check your answers. In the atomic structure topic, there are a number of facts that were examined in GCSE chemistry, but they're then going to be examined again in the AS papers, so it's important that you're absolutely secure in these. So we start with the relative charges and the relative masses of the three subatomic particles, and you know that wherever you see the word relative, you need to be giving this in a numerical form, not just saying positive or negative. So protons, of course, have a charge of +1, electrons -1, and neutrons are neutral, so that's 0. And then in terms of the masses, protons have a mass of 1, electrons are about 1/1840th of the size, and neutrons also have a mass of 1 because they're approximately the same size as a proton. John Dalton's model was that billiard ball model where he described atoms as being hard, indivisible spheres. And then J.J. Thomson developed the plum pudding model after he discovered the electron. So we've got this mass of positive charge with these negative electrons contained within it. So it looks a bit like a plum pudding or a Christmas pudding. If we compare that plum pudding model with the nuclear model, firstly, the plum pudding doesn't have a nucleus. And of course, that means it also doesn't have any neutrons. And then also the plum pudding model doesn't have any shells because the electrons are inside that ball of positive charge. The nucleus was discovered by Ernest Rutherford and his students when they carried out the alpha scattering experiment. Niels Bohr then went on to adapt the nuclear model because he said that the electrons didn't just go wherever they wanted to, they orbited the nucleus at fixed distances. So he basically added in shells. Then in 1932, James Chadwick discovered the neutron, and this was important because it implied the existence of isotopes, and that allowed us to explain mass data. So for instance, why is the relative atomic mass of chlorine 35.5? Oh, it's because there are two very commonly occurring isotopes. Isotopes are atoms that have the same number of protons, so they're intrinsically the same element because that's how we define an element based on its number of protons, but they have different numbers of neutrons. If you have a pair of isotopes, then they will have the same chemical properties, and the reason for that is that the chemical properties are dictated by the electrons. And as we've established, isotopes have the same number of protons, and therefore in their atomic form they'll have the same number of electrons, so they have the same electron configuration. In other words, their electrons are in the same places, and since that's what controls the chemical properties, those will be the same. In contrast to that, the physical properties of a pair of isotopes may differ. So for instance, the mass is definitely going to differ, but also they may differ in terms of things like how radioactive they are. And that's because they have different neutrons, which are going to make them heavier and are also going to affect the stability of their nucleus. There are a couple of different ways that you can define relative atomic mass, depending on whether you want to talk about atoms or moles, and either one is fine as long as you're being consistent with yourself within your definition. And whichever one we're talking about, we're comparing it to 1/12 of the mass of the carbon-12 isotope, which as we know is the reference standard. So I would be saying that the relative atomic mass is the weighted average mass, in other words, we're taking into account the relative abundances of the different isotopes, of an atom of an element, compared to 1/12 of the mass of an atom of carbon-12. But as I say, you could take out the word atom and replace it with the word mole, and that definition would still make sense as long as both of the atoms became moles. Now, relative atomic mass and mass number are not exactly the same as each other, because relative atomic mass, as we've said, is a weighted average of all the different isotopes, whereas the mass number applies to one particular atom. And that means that the mass number will always be an integer because there always have to be an integer number of protons and neutrons, and that is how we define the mass number. Whereas if an element has more than one isotope, then we would expect that it's quite likely that the relative atomic mass will not be an integer. Now, it's actually quite hard to write an annotated calculation for this kind of question without giving you data, but I did promise that these were pure factual recall questions, so I tried to stick to that. So if we've got two different isotopes, A and B, so they're the same element, but actually we're using the A and B to show they have different mass numbers, and A makes up X% of the sample. Well, the first thing we can say is that A is X%, but personally I prefer working as decimals, so I'm going to do that as 0.x. You could also do X over 100, and that would be functionally the same thing, but this is just my preferred way of working. And so if A makes up X% and we know that there are only two isotopes, then B must make up 100 take X%, or we could express that as 1 take away 0.x if we're going to work in decimals. So then our expression for the relative atomic mass of this sample would be 0.x multiplied by the mass of A plus 1 take 0.x, so in other words the abundance of B, times by the mass of B. Now, if that didn't make a huge amount of sense, hopefully it will if we add some numbers in. So let's say that A is the mass of 30 and B is a mass of 31, and 40% of the sample is A. That's therefore going to mean that we need to do 0.4 times 30, because the abundance of A is 40% and it has a mass of 30, and then 0.6 times 31. And those numbers added together would give us the overall relative atomic mass. The 5 stages in time-of-flight mass spectrometry are firstly ionisation by one of two methods, then acceleration of the different ions until they have constant kinetic energy, then drift, then detection when they hit the negative plate, and finally analysis. To carry out time-of-flight mass spectrometry, there are 2 ways that you can ionise the sample. So firstly, there's electrospray ionisation, and in this the sample is going to be dissolved in a volatile polar solvent. So that could be something like water or methanol, and then that sample is going to be injected through a very high voltage needle. And you don't need to know a particular voltage, but if you wanted to quote one, it would need to be something in the region of about 4,000 volts. Now, when that happens, the sample gains a proton, and so it becomes positively charged, and also its MR increases. Our second way of ionising the sample would be electron impact, and in this the sample is vaporised, and then we fire high energy electrons at it, and these basically knock off an outer shell electron, so it still becomes positively charged, but the mass doesn't change. So if we compare the ions that are produced by these different methods, for electrospray, as we say, we're adding a proton. And so this is going to make an ion that is equivalent to M, where M is your starting atom or your starting molecule with H+ on it. Whereas for electron impact, we're taking away an electron, and therefore we're just getting an M+ ion. So as you can see, both of those are positively charged ions, but the difference is in what happens to the relative formula mass. So for electrospray ionisation, the relative formula mass increases by 1, but in electron impact, the MR is going to stay the same. M over Z stands for mass divided by charge. So this is going to be the mass to charge ratio. And usually the charge would be a single positive charge. So usually the M over Z ratio is actually going to be equivalent to the mass of your sample. However, it is possible for an ion to have an MZ value that is half of its mass, and that will occur if it becomes double charged. In order to calculate the kinetic energy of an ion, we do half mv squared, where m is the mass in kilograms and v is the velocity that the ion is moving at. The isotopes reach the detector at different times because even though they have the same amount of energy, they have different masses. So although Ke is constant, the smaller mass will lead to a faster velocity. When the positive ions reach the negative plate where they're detected, their positive charge is going to cause the negative electrons to move to join them, and that causes a current to flow. And the size of that current can be used to determine the abundance of a particular isotope with a particular mass. Now, although our regular time-of-flight mass spectrometry won't allow us to distinguish between compounds that have the same relative formula mass, if we're using high-resolution mass spec, then we can tell the difference. And the reason for that is the greater degree of precision. And high-resolution mass spec is sufficiently precise that we can tell that hydrogen isn't actually exactly 1/12 of the mass of carbon. And so where compounds have different elements in them, we can actually detect that in the mass spec. First ionisation energy is the energy change that you see when 1 mole of gaseous atoms lose 1 mole of electrons to make 1 mole of positively charged ions. And that word gaseous is really, really important here. So when you write your equation for the first ionization energy of an element, there are a couple of different ways you can do it. The most common would be like this, so where we've got a gaseous atom splitting apart to be a single positively charged ion and also an electron, but it's also okay if you want to write it showing that this is being carried out because an electron is effectively removing another electron. So we can have our initial gaseous atom and one electron, and then the ion and two electrons. But whichever one you go for, it's absolutely vital that you're adding in those state symbols, and you won't get the mark if they're not there. It does usually say in the question including state symbols, but even so, we really regularly see students missing them out, so make sure you have those. As you move across period 2, from lithium to neon, the overall trend in first ionization energy is that it increases. And the reason for this is that as we go left to right across the periodic table, each new element has one more proton, so we're increasing the amount of nuclear charge. However, as the nuclear charge is increasing, what we're not doing is adding any more shells, so there's no difference in the shielding. Usually when this question comes up, you need to talk about both the increased nuclear charge and the lack of more shells in order to get 1 mark, so it's really important that you include this. If this isn't making sense, contrast it with as you go down group 1. So as you go from lithium to sodium to potassium, you're still adding more protons, but you're also adding another shell, and that means more shielding. So that outer shell electron is actually more easily lost, and that's why as you go down group 1, it gets more reactive. We also need to talk about what the attraction is actually between. So there's this stronger force of attraction between the positively charged nucleus and those negatively charged outer shell electrons. There are, however, 2 exceptions to this overall trend. So the first one is that the first ionization energy of boron is lower than beryllium even though it comes after it. And this is because of where that outer shell electron is. So the final electron in boron isn't in the 2s subshell, it's in the 2p subshell. And this is a higher energy subshell than 2s, and this means that that electron is more easily lost. The second exception is that oxygen has a lower first ionization energy than nitrogen, even though both of their outer shell electrons are in the 2p subshell. But the reason here is that in oxygen, we start to see those electrons being paired. So the 2 electrons that are in the 2p are paired together and they are repelling one another more. It's important that you specify that it's the paired electrons that are repelling each other more than the other electrons, because nitrogen still has electrons and they're still repelling each other, just not as much as the 2 that are sharing an orbital. The beginning of the periodic table is made up of the S block, followed by the P block, followed by the D block. And elements are assigned to these blocks based on where we find their valence electrons or their outer shell electrons. The S subshell can contain 2 electrons, while the P subshell can contain 6, and the D subshell can contain 10. Each orbital within these subshells has room for 2 electrons. As we're filling electrons, we fill the 4s subshell before the 3d subshell, but then we also empty it first. Finally, we're going to take a quick look at writing out the electron configuration for some different atoms and ions. So starting off with potassium, you should have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, because of course we fill 4s before we fill 3d. Then for scandium, this is a D block element, so we are going to get to that 3D. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. It's up to you whether you want to write the 3D first or the 4s first. Either one is fine as long as they're both there. Now for this vanadium ion, we're just going to look at how we get to where we get. So I'm going to start off thinking about a vanadium atom. This is element number 23. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. However, when we start removing electrons, remember, although we fill 4s first, we also empty it first. So those 2 electrons are going to be taken out of the 4s subshell, not out of the 3d subshell. When it comes to placing electrons and we're thinking about chromium and copper, these 2 elements are important. And the reason for that is that the 3D subshell, it's more stable to have D5 or D10, much more stable. And so if you're in a situation where you would potentially have D4 or D9, You just don't go there. So instead of having D4 or D9, you take one of those electrons that was in the 4s subshell and you use that to top up to 3D5 or 3D10. So when you look at chromium and copper, you're going to see 4s1 in the atom, not 4s2. Hopefully you found that a useful way to recap the key facts from the atomic structure topic. This is one of a series, so if you did find it useful, let me know in the comments below, and like and subscribe for more A-level chemistry content coming soon.